All right, so we're going to talk about plate tectonics. This is one of my favorite things to learn about. Plate tectonics is the movement of large sections of the Earth's crust. And it really started with Alfred Wegener back in the 1800s, late 1800s actually, well, I guess early 1900s. And he was a meteorologist. He actually studied the weather. And he noticed that continents looked like they fit together like puzzle pieces. And so that started him off on this journey of really proving or trying to prove that at one time all the continents were joined together in a super landmass called Pangea, and that the continents separated into where we know they are today. But he could never really prove why that happened, and he ended up dying actually on an expedition to Greenland. He ended up getting lost and freezing to death. And just a little known fact, his body is actually still out there to this day. So in the 1970s, we started exploring the ocean floor for oil, and we looked at sonar maps from the 1940s, World War II, and we began to see that the mid-Atlantic Ocean, in the middle of the Atlantic Ocean, is pulling apart, seafloor spreading. The bottom of that ocean is pulling apart. And we began to understand why that happened. And that became the theory of plate tectonics. All right, so the plates do not look like our maps of continents and oceans. Actually, plates can have oceans, just oceans on them. They can have oceans and continents. So, for instance, here is the Pacific plate, and you can see it's huge, and it has the Pacific Ocean. You've got the Nazca plate here, which is also an oceanic plate, the South American plate, which has also got part of the Atlantic Ocean in South America, and these plates are huge, and they are moving around. And so they're sitting on top of the mantle. And the mantle is made up of magma, which is melted rock. And it's thick enough, it's kind of like pudding. It's thick enough that it supports the lithosphere, so the lithosphere doesn't just sink down through it and melt into magma. And it's also thin enough that it allows these plates on top to move. And the reason why they move is because of convection. Right here, convection currents, that's really the big secret to Earth science. And that is understanding that as you get closer to the outer core, it gets really, really hot. And I wish my mouse would write better. Whereas as the closer you get to the crust, the cooler that the magma gets. Now, don't get me wrong, it's still very, very hot, but it's not as hot as it is closer to the outer core. And we know that warm things rise and cooler things sink. And so as that magma gets close to the core, it gets superheated and it begins to rise to the surface. And as that magma rises, it loses heat, and things that lose heat and become cooler begin to sink back down, and it starts this whole process of convection. And so you can see here, this convection current is pulling to the left, whereas this convection current is pulling the plates on top to the right. And so what happens? You get these two plates are pulling apart, they're diverging, and magma seeps up through and cools in the ocean and solidifies. It gets hard and igneous rock, and over thousands of years you'll get these enormous mountains underwater, and we call those ridges. And we'll talk more about that in a moment. So, we're really interested in plate boundaries. I'm really not interested in what's going on here in the center of a plate. I'm really interested in what happens at boundaries and what direction these boundaries are moving, because that's what creates land features here on the surface. So in a transform boundary, we have plates that are sliding past each other. In a divergent boundary, the plates are being pulled apart. And in a convergent boundary, the plates are pulling together. And so I remember it by doing the cheer. Convergent, divergent, transform boundaries. All right. So, what is a transform boundary? Well, a transform boundary is where two plates slide against each other. But really, what you've got to know is the land features that are formed at these boundaries. And so what happens? We get earthquakes and we get faults. And what are faults? Faults are huge cracks in the ground. As a matter of fact, the largest fault in the world is right here in North America, in California, and it's called the San Andreas Fault. And you can see here in this picture where this plate's going this way and this plate's going this way, and you end up with a crack. And that is a transform boundary. All right, divergent boundaries, or plates are moving away from each other. And two things can happen here. When I have a continental to continental plate, that means that at that boundary there's a continent sitting there. So when I have two continental boundaries and they are pulling away from each other, they're going to create rift valleys. And the most famous one is the Great African Rift Valley. They form a rift valley, a valley where the ground is sinking down because the plates are pulling apart. When I have an oceanic and oceanic plates where oceans, the boundaries where the oceans are pulling apart, I get those beautiful mid-ocean ridges, which are underwater mountains. And in the middle of the Atlantic Ocean, those mountains are so big under the water we can actually see them from space, even though they haven't even come close to breaking the surface yet. The Atlantic Ocean is getting bigger. And if the Atlantic Ocean is getting bigger, then that means that the Pacific Ocean is getting smaller. And that's what happens where two plates are pushing up or colliding against each other. So anytime I have an oceanic plate, either it's oceanic and oceanic plate that's colliding or an oceanic and a continental plate colliding, it doesn't matter. If there's oceanic, there's a process called subduction going on. Subduction means to go, sub means below, subduction. And actually that plate will be dragged right here down into the mantle and it will melt and turn into new magma, which is actually very cool. And what we get are volcanoes right here where the pressure is forcing this magma up to the surface. And we also get this kind of an underwater valley, and that's called a trench. A trench. So volcanoes and trenches are formed anytime there's subduction, if there's an oceanic plate that's colliding. When I have two continental plates that collide, two continents that are colliding, we get these huge mountains. And actually the Himalayan mountains, where the Indian and the Eurasian plate are colliding, is still happening to this day. The Himalayan mountains are some of the tallest mountains on the surface of our planet. Surface meaning land. The tallest mountains, of course, are underwater, these mid-ocean ridges. But on continents would be the Himalayas, and that is formed because these two continents, continental plates are colliding together. All right, so what type of boundary do I have here? I have a convergent boundary. And what landform is created there? Well, if I have oceanic plates colliding, I'm just going to put oceanic here because it's really hard for me to write with this mouse. We're going to get volcanoes. We're going to get subduction. And we're going to get volcanoes. You can hear me growling because I'm getting frustrated with this. But we're going to get subduction. So we're going to get volcanoes and those really pretty underwater valleys, which are called trenches. Now, if I have two continental plates, I'm just going to put continental here because it's too much to write for me. But continental plates colliding, what am I going to get? I'm going to get those really tall mountains. Okay? This is a transform boundary. And what landform is created here? I get faults. And those are those big cracks in the ground, which are caused by earthquakes. I don't know if it's better for me to do cursive or print, but earthquakes. Okay, and what type of boundary is this? This is a divergent boundary. And a divergent boundary, to diverge means to pull apart. You know, there was a movie that just came out not too long ago called Divergent, meaning that you're going apart. You're pulling apart. And so landform created by this movement, well, if I'm in the ocean, I'm getting, especially in the middle of the Atlantic Ocean, I'm getting those beautiful mid-ocean ridges, which are those underwater mountains. I really do apologize for this scribble. It seems like it's getting worse, but that's okay. All right, continental plates that are pulling apart, we're going to get these really cool rift valleys. All right. Whew, okay, on we go. Which table. Oh, let me get my highlighter out. That looks like a question. Which table represents a land feature or geological process that occurs at each type of boundary pictured? Well, let's look here and see. I have my pen. So, I'm assuming this is Q, R, S, and T. That should have been labeled. Okay, I know that T is a transform boundary. So what's going to be formed at a transform boundary? Earthquakes, and I know that. So see, I went for the easiest one that I knew first. So I'm going to get rid of anything where T is not there. Boop, boop, gone. Okay. I know this is two continental plates. It's not an ocean. This is two continental plates, and they are colliding. And I can actually see the mountains forming here. So S is going to be a mountain. And do I have that mountain right here? Yes, I do. So I'm going to get rid of this, but I'm going to double check. In subduction, which is R, do I get volcanoes? Absolutely, I get volcanoes and trenches. And here I have two oceanic plates pulling apart. I don't even have to have the water there. I know that that's a mid-ocean ridge that's divergent. My best answer choice is A. So, it's important to know the land features that are formed at these boundaries. All right, moving on. Which of the following statements is not... Ooh, I need to definitely make sure I get that. Is not supported by plate tectonics theory. Okay, so what is not supported by plate tectonics theory? Continents move through the seafloor crust. I have no idea what that means. Let's come back to it. Locations of volcanoes and earthquakes can be explained. That is true. So that's plate tectonics. Seafloor spreading provides evidence. That is true. That is plate tectonics theory. There are 3 different types of plate boundaries. Yes, that is true. And I have no earthly idea what this means. Continents don't move through the seafloor crust. Continents are actually on top of, well, they're not even on the bottom of the ocean, so that made no sense. Okay, let's go on to this question here. Many scientists believe convection currents in the mantle between South America and Africa caused the separation of the 2 continents and the formation of the Mid-Atlantic Ridge. Which diagram best represents convection currents in the plate tectonic theory? So we're looking for Mid-Atlantic ridges. And let's see, I'm looking at, so I know in a mid-Atlantic ridge, I have divergent boundaries. So look at these arrows right here. Does that even make sense? No, because that's convergent. This is transform. This is convergent. I mean, this is convergent right here, so that can't be right. And that's not even a convection current, because your convection currents, remember, are going to go in a circle. So your best answer choice is where they're diverging. Absolutely. And you have a nice convection current here. This one's pulling the plate to the left. This one's pulling the plate to the right. All right. Good job, guys. Topographic maps. The most important thing to know about a topographic map is this right here, that the contour lines are showing you elevation. Okay. It's how steep something is. So when the contour lines are close together, the slope is steep. It's going to be a tall mountain. When the contour lines are far apart, the land is getting flatter. I actually use this in the military. That's how you find out where you're going in the military, is through a topographic map. All right, the top of this drawing is a topographic map showing hills that are illustrated at the bottom. The vertical distance between each contour line is 10 feet, which means that the contour interval is going to be what? 10, 20, 30, 40, 50, and it is indeed 50. So 10 feet is going to be my contour interval. So which is higher, A or B? Well, I can kind of look at the map and see that, right? It's definitely going to be B, okay? Which is steeper? Well, these lines are closer together on B, so B is going to be your best answer choice. Remember, contour lines that are close together show steeper elevation. How many feet of elevation are there between contour lines? 10. 10 feet is a contour interval. How high is hill A? Well, here's A, and we could say 40, but we got to be careful here because we still have that space in between, okay? If the only answer choice you have is 40, then 40 would be your answer. But technically, if you had another contour line here, it'd be 50. So your best answer choice is somewhere between 40 and 49. Okay? So, if you have an answer choice that's 49, that is the correct answer. If they just give you an answer choice of 40 and some other random numbers, then go with 40. How high is hill B? Well, again, if I had another contour interval here, it'd be 60, so I got to go one down. So this is going to be 50 to 59. Because we don't have another contour interval there, we're not really sure. It could be anywhere in that range. Are the contour lines closer together on A or B? Well, they're steeper on B. So your answer choice was B. And you may get a question like this where you're looking at a map and then looking at how they put it in topography in a two-dimensional form. All right, let's match these. So here I have a pretty I have a mountain here. I have a hill. Ooh, this is a very steep drop-off. Do you see this? So this goes with this because look how close these contour lines are together. So that goes there. Here I have a drop-off, and then I have another hill in the background, don't I? Right? So I've got this hill, and I have the steep drop. So here's my close contour lines, and here's my hill. Here I've got a river running through. So normally my river would be a V shape, but here they actually put a river in here for me. Actually, it looks like a road. So this must be the road here, and this is the road here. And you can kind of see these V shapes, which is the river. Okay, so that leaves me this peak right here, and that is to this topographic map. All right, guys, good job. Let's answer this question right here together. We're going to highlight this. Based on the information above, what is the following is a valid? Valid means true. What's a good conclusion there? Well, I got to figure out what's going on. So the Salzburger Ice Shelf is a large ice formation in Antarctica. It's about 8,000 miles south of Japan. It's 85 miles long and 50 miles wide, so it's pretty big. In March 2011, the Salzburger Ice Shelf had not moved for nearly 50 years. The two satellite images to the right show the Salzburger Ice Shelf after an earthquake and the resulting tsunami, which is a tidal wave, that occurred near Japan on March 11, 2011. The earthquake measured a 9.0 in the Richter scale. That was a serious earthquake with a serious tsunami that did a lot of damage. So let's see what is a valid conclusion. The force of the earthquake and tsunami on March 11th was limited to areas near Japan. Well, that's not true because it just said it's 8,000 miles south of Japan. And look at what's happened here. Look how much of the shelf has broken off. Look how much ice has broken off as a result of that earthquake. Holy smokes. Events like earthquakes and tsunamis have the greatest impact on areas south of the actual events. That's not necessarily true. It could be north, could be east, could be west. Just depends on the direction that the energy from that earthquake is traveling in the ocean. The force of the earthquake and tsunami on March 11, 2011 had far-reaching consequences. It absolutely did. The Salzburger Ice Shelf in Antarctica was already weak and therefore likely, well, no, because it says here that it hadn't moved for nearly 50 years, so obviously it wasn't weak. So your best answer choice was C. And it is true. Very far-reaching consequences with that. All right, study the diagram above, and that is going to show you an island before and after a hurricane. So I've got before and after a hurricane. What most likely caused the changes to the island? So what changes do I have? Well, I've got to look at the beach. Let's look at the beach here. This is the beach. So before the hurricane, I had lots of nice beach here. After the hurricane, woo, I have very little beach. So the rainwater from the hurricane raised the level of the ocean? No, that would be scary. The island sank deeper into the ocean during the hurricane? No, islands don't just sink. No matter what movies show you, they don't just sink. Ocean waves caused by the hurricane eroded sand from the beaches. Oh, I like that word, eroded. Carried the sand away. Ocean waves. Yes, that's definitely possible. Rivers on the island deposited new sand on the beach? Well, if that was true, then I would have more beach area, not less. So your best answer choice was C. And that's exactly what happens in hurricanes. The ocean waves carry the sand out into the ocean and the beaches get smaller. What does a grouping of close contour lines indicate? Well, we know that close contour lines means steep. So your answer was C. Water? No. Meadow, they'd be spread further apart. A meadow is flat. A railroad would have tracks on it. So no, a steep slope, steep, close contour lines. A student used the topographic map to plan a hike. Okay, wanting to hike. What information is shown by the contour lines? So what can I see? Well, this question's pretty easy. It's asking you what's the whole purpose of a topographic map? And that's elevation. It is not distance. It's not foliage, which is trees, or parking spaces. It's elevation. How tall, how steep something is. And if I'm hiking, I want to have far apart contour lines because that means it's flat land, which is easier than a tall mountain. All right, what would you look for in a series of topographic maps that determine erosion has occurred? Erosion has occurred. That means carrying sand away. Widening of the spaces between the contour lines. That means the land is getting flatter, and that's exactly what happens with erosion. That's a possible answer choice. Increase in the number of rivers? No. Wind speed? What does wind have to do with topographic maps? A crossing of contour lines. That doesn't even make sense. Contour lines don't cross. So a widening of the spaces between the contour lines, that means the land's getting flatter from erosion. Good job, guys. Well, good luck on this. Take your time, and remember, contour lines definitely show you elevation.